sharing my screen. I thank ISAMP for giving me this opportunity. I think this web series has been quite a successful way of keeping the momentum going even in these difficult times. And we have heard quite a few nice talks in the last 2 months. The set of talks that we heard were somewhat different from the usual set of talks that we hear in ISAM conferences, because we could get a diverse set of people onto this platform. And I hope that we continue this trend and get reach out to wider number of people, and also get much more information, much more diverse information about fields that are not traditionally atomic physics. So today's talk is perhaps one in a similar vein. I'll be talking about the design, construction, and eventually the launch of an ion spectrometer for observing the solar wind. So this is really a talk about much more about the instrument than about the mission itself. And as you will see, that lots of things that we study in the course of our experiments to understand atoms and molecules actually help us design instruments that could be used in diverse fields. And one such field is solar physics. This project has been going on since 2013. Since 2013 was, yes, that was the first time that we thought about this, and the mission was launched or declared, not launched. And since then we have been working with various, many variations to finally come to a stage where we are confident that we can launch an instrument. This project is a mega project in a sense that it involves people from multiple institutions. So although I am currently at ISAP Pune, this project really started when I was at PRL in 2013. There's a big team at PRL which is doing most of the job, and I am merely speaking on their behalf. There's a whole team at ISRO which looks at the logistical aspects, really the difficult part of making things space worthy. It is a very long journey from an idea of an instrument to really building an instrument which will eventually fly and work. And I hope that during this next hour, or a little less than an hour, I'll be able to impress upon you the difficulties involved and the challenges that we have to face on the path. So let's begin. Let's begin by looking first at the connection between solar physics and atomic physics. So this might seem like a very tenuous connection, but you will see very soon that it is not as tenuous as it seems. So if you look at the solar spectrum, when I say the spectrum, I really mean the visible spectrum. So in the visible spectrum, one of the most prominent lines is this so-called H-alpha line. The H-alpha line is the n is equal to 3 to n is equal to 2. So the 3p to 2s transition in the hydrogen atom. And hydrogen is the most abundant element in the sun. And transitions in the hydrogen atom are actually very, very useful for us to study a lot of things about the sun. One of the most important things that has been studied using this transition is a study or a mapping of the magnetic field of the sun. So you know that if a transition in an atom couples two different ML states, then the application of a magnetic field splits this line. So the Zeeman effect, which splits the spectral line into multiple lines, is indeed a measure of the magnetic field. So using this idea, the magnetic field of the sun has been mapped in extreme detail by merely observing the polarization and intensity and the splitting of the Zeeman splitting of the H-alpha line in the hydrogen atom. But this part, what I just talked about, is the optical part, where you try to observe the sun using the light that comes from the sun. But there's another component to the sun, which is the particle component. The particle component is the emission or the spewing of protons that is constantly happening from the sun. The sun is constantly emitting protons in all directions. And the very curious and a very interesting part about this whole process is that when these protons are emitted from the sun, these protons are essentially free. I mean, the number densities are so small that you could just think of these as as free currents flowing out of the sun. Okay? No hindrances. Now, this solar wind, or this stream of particles that comes from the sun, containing mostly protons and a little bit of alpha particles. This proton and alpha particle mixture pervades the interplanetary space. But this solar wind doesn't enter the Earth's atmosphere because it gets shielded or deflected by the magnetic field of the Earth, the magnetic shield, and it is also, and whatever comes through is also absorbed by the Earth's atmosphere. So the Earth's magnetosphere and the Earth's atmosphere together make sure that the solar wind never reaches us, except in very rare cases where you start seeing phenomena like aurora borealis or aurora australis. But these are only very rare events; they cannot be reliably observed, and these are only seen in extreme polar regions. So, if you really want to study the solar wind, it becomes essential to establish an observatory outside the Earth's atmosphere. So, which clearly means that you need to have a satellite-based platform. And you could go far away from the Earth, or you could have a satellite that orbits around the Earth. But an orbiting satellite has a problem that it will not see the sun for half the time. And depending also on the orbit, some of the fields of view may be not very suitable for making very prolonged observations or observations of a specific nature. So, the most advantageous point, most advantageous position for this system is this point called the Lagrangian point. So if you draw a line connecting the center of the sun to the center of the Earth, on this axis lies a point where the gravitational attraction of the Earth and the sun cancel each other. So this point is called the first Lagrange point. I mean, the definition of the Lagrange point is slightly different, but for the Earth-Sun axis, as shown here, this is equivalent of that. It is the point where the two gravitational forces cancel out. At this point, the Lagrange point, if you place an observatory, then you have an uninterrupted view of the sun. And this observatory, which is shown by this green rectangle at L1, will constantly keep observing the sun and keep on co-moving with the Earth. Now, this Aditya L1, which is a mission to place such a satellite or such an observatory at the L1 point, is ISRO's first solar observation mission. Unlike the missions of the past, this mission is an entirely quote-unquote scientific mission. It does not have any remote sensing or communications kind of purpose, which is very often the case in ISRO's mandates. But this one is a purely scientific mission, like the AstroSat, which was launched last decade. Okay. Now, this spacecraft will be permanently settled or located at the Earth-Sun Lagrange point, and it will not remain stationary. I mean, unlike what we would like to think in the ideal situation, this satellite is not going to stay at one point on the axis. It is actually going to carry out a halo orbiting, a pretty random, well, not random, but a Lissajous figure kind of movement around this Lagrange point. It will point continuously toward the sun, and ISRO engineers are very confident of making this pointing accuracy extremely high. So it will be so good that it would be possible to obscure the sun obscure 1.05 times the sun's diameter at any given point of time. So the launch schedule is sometime next year. This spacecraft is expected, or is going to weigh 1950 or 70 some such kilograms, a little short of 2000 kilograms. And it will be launched using the PSLV-XL vehicle, which is ISRO's most reliable and powerful, one of the more powerful rockets. And it will need a 180-day journey to reach the L1 point, which is 1.5 million kilometers away. Now, what do we have on this satellite or on this mission? So this mission, as I said, is essentially a scientific mission, and it has many instruments which are going to do a variety of observations of the sun, not just the solar wind that I mentioned, but also visible emissions, ultraviolet emissions, X-ray emissions, and so on. So this is the list of instruments that will be flying on the L1 mission. I have highlighted the Aditya Solar Wind Particle Experiment, or aspects, since this is the instrument that I'm going to be talking about. So this is how the satellite looks, or will look when it is assembled. This is a satellite with 2 solar panels. We are seeing this satellite as if we were looking at it from the sun. So think of it as, think of yourself as the sun, and this as the satellite. So this is the largest payload, called the VLC. There is the second payload called suit, which is not seen here. It is hidden somewhere under this. And there are 2 smaller payloads called steps here and Swiss here, which together form the aspects payload. So these are really small payloads compared to the size of the satellite. So much of the satellite mass is actually needed for navigation, for communication, for maintaining temperature, and so on and so forth. So the instruments actually constitute only a very small fraction of the total weight of the satellite. And the VLC and the suit, which you see here on the side, these 2 are large instruments. They weigh, if I'm not mistaken, the VLC weighs about 130 kg and the suit weighs 60 kg. And our payload, which is Swiss, which is shown here, weighs only 12 kg in all. So it's really a small payload. Okay. Now, is this the first mission to the sun? No, it is not. The very first mission to the sun at the L1 point is this ACE, which was launched by NASA in the 70s, and it has been there since 1978. There's another satellite called WIND, which was launched in the 80s, and it is still functioning. Then there are some more recent satellites like Stereo, SOHO, Discover, which are not all at L1. Some are at L1. The Stereo satellite is actually a pair of satellites, and they keep orbiting the sun in a certain orbit, such that these 2 satellites are always 180 degrees out of phase. Then there are other satellites which at L1. Some of them are 3-axis stabilized. When I say 3-axis stabilized, it just means that the satellite doesn't need to remain spinning in order to stay stable. It has mechanisms to maintain its attitude all through its lifetime. Aditya L1 is again going to be at L1. It is also 3-axis stabilized, so it can point to a specific direction with very high accuracy all through its lifetime. So it can look at different directions from L1 without having to worry about whether the satellite will lose track of the object or not. In terms of what we are going to do, or what we are going to add to this mission, is that our instrument will add the ability to differentiate between protons and alpha particles that come from the solar wind. And I'll come to the details of this in a while. Okay. So the Swiss instrument, which is really the instrument that I'm going to talk about, which is a short form for the solar wind particle spectrometer, or ion spectrometer. Sorry, it should have been ion, not particle. It is designed to measure 2 things. It is designed to measure the angular distributions and the energy distributions of the solar wind. So different directions, as well as the kinetic energy distributions. In addition to this, it will separate protons, alpha particles, and other heavy charged particles over a fairly high range of energies. And the Swiss instrument alone just weighs 8 kg. And the companion instrument STEPS, which is meant for studying even higher energy protons and alpha particles using solid detectors, is an instrument that will co-fly. But that's a much smaller instrument. Okay. And my focus is going to be on this Swiss instrument. Okay. So before I go into what the instrument does or how the instrument is constructed, I just want to draw your attention to how the solar wind propagates. So this is a picture that shows something spiraling out. Now, what is this thing that is spiraling out? As I told you earlier, the protons that are emitted from the sun are actually expanding freely. There is no atmosphere in their path. So you can think of these as free currents in vacuum. Now, any free current will generate a magnetic field. So all of these, each one of these protons is actually generating a magnetic field. And because of this, every proton feels a magnetic field because of itself and other protons. So, and as a result of this, as a result of this very strong coupling between the current and the magnetic field, the proton path actually spirals out. And this is called the Parker spirals, after Eugene Parker, who realized this and made this model. Okay. So the average wind of the average speed of the solar wind, or the mostly the protons, is about 400 kilometers per second, and this magnetic field is of the order of nanotesla. Now, this magnetic field and the proton flux pervades the entire interplanetary space, and it has an extremely high conductivity. There is nothing else but charged particles there. So, any observation of this solar wind is really like an experiment where you're counting particles. Any experiment that is aiming to count to study these protons essentially is to count these protons, find their velocities, look at the directions in which they are going, and so on. And that is where our experience in atomic physics, in building experiments for studying atomic processes, comes in very handy. Now, what is the energy distribution of these instruments? Namely, the data from WIND and ACE have shown us that the distribution of the proton energies is something like this, as shown in this diagram. So this is from a paper by Mason and Glockler in the 80s. And this shows that the flux peak of the solar wind is at an energy of about 1 keV. So this is in MeV per nucleon. So this is about 1 keV. And the flux is quite high. It is 10 to the 16 per centimeter square per steradian per MeV at the peak. And if you look at the shape of the distribution, this shape is a very odd shape. You cannot fit a single distribution to that. If you fit multiple Maxwellians followed by a power law for the tail, then you can approximate this by 2 or 3 Maxwellians and 1 power law. And if you average the kinetic energy, or find the Maxwellian temperature for this, then the Maxwellian temperature actually shows a directional dependence and a magnetic field dependence. So now this is really the curious part. So you take this distribution, and let's say you just look at the mean kinetic energy. So the mean kinetic energy shows a dependence on the direction of the particles, and it also shows a dependence on the local magnetic field, meaning depending on where in the interplanetary space you measure this, you get a different distribution. So to quantify this, solar physicists define a quantity called beta, which is the kinetic energy of the particle divided by the magnetic energy. So the magnetic energy is simply b squared by mu naught, or 4 pi by mu naught, something like that. So it's kinetic energy by the magnetic energy. And you can then define 2 kinds of betas. So there's a beta perpendicular and there's a beta parallel. And this ratio, beta perpendicular, where is the value of this ratio for particles that are streaming perpendicular to the local magnetic field, and beta parallel is the same ratio for particles streaming along the local magnetic fields. And you find that these are very strongly correlated. Okay. So if you are able to measure a local magnetic field and measure the particle kinetic energy at the same location, you can find this beta, and you can find beta perpendicular and beta parallel if you also have directional measurement capability. Now this, if you start looking at this a little more carefully, you find that this is not exactly at 45 degrees. It shows a slight deviation from 45 degrees, which means that there's an anisotropy. And you can see that there's an anisotropy, and there's greater population in the above the diagonal. And solar physicists who model the plasma, do the magnetohydrodynamic calculations for the solar wind, believe that this anisotropy, or if you are able to measure this anisotropy, it will help them establish different models of the solar wind, and also be able to say how different energetic processes happen, which throw out, or which lead to coronal mass ejections and different energetic processes on the surface of the sun. So the measurement of this beta is an important parameter for establishing models of the solar wind. So the solar wind, and in particular, I should say that there is one more parameter that is important, which is the ratio of the number density of the alpha particles to the number density of the protons. So this proton alpha ratio is typically small. I mean, in the quiescent solar wind, this is about 8%. But whenever there is very heavy activity on the sun's surface, this activity could be called solar flares or coronal mass ejections, depending on what kind of activity it is. So coronal mass ejection means large masses, large amounts of matter being thrown out of the sun, and and flares are basically similar activities happening close to the surface of the sun. So in both these cases, this ratio changes. And the reason why this ratio changes is that the energy of the sun is driven by a thermonuclear process, which results in a fusion, which is a fusion reaction resulting in the creation of alpha particles. And an enhancement of the alpha to proton ratio is a sort of indirect proxy for the solar activity. So this number has been measured in great detail by various missions and various workers, and its importance has been established. So this is the background against which we set out to do our to design our payload, and these are some of the questions that we try to address using this instrument. So the first one is that if you look at the suprathermal ions and the subthermal ions, and in this case, thermal just means below the peak and above the peak of the distribution. So how does this distribution shift when there are solar energetic particle events? So SCP is just this common name for all kinds of energetic processes. So how does this distribution change? That is one question that we would like to answer. Then we would like to answer the question of correlation between solar events and changes in this proton to alpha ratio. And the third thing we would like to answer is how does the anisotropy change, the anisotropy in the energy distribution. Now remember that this is not an anisotropy in the usual sense of the term. It is an anisotropy in the energy distribution. So the energy distribution of particles along the direction in which the orbital plane lies or the ecliptic plane lies, and the direction perpendicular to that. The energy distributions in these two directions is what we are looking at. The difference is what we are looking at. So it is an anisotropy of the energy distributions, not just an anisotropy of the flux. So how did we go about deciding what to do? So these are the three quantities that we were interested in, or these are the three parameters, if you like, that we were interested in. And we then started looking at what exactly would we need to observe in order to address questions related to the left, questions listed out on the left. So for the first part, we realized that we would need to measure, obviously, the energy distribution, the E/Q ratio, for all particles reaching the instrument over a range of 100 eV to 20 keV. The second thing we would like to do is measure the species-dependent angular distributions. So we would like to establish the thermal or the energy anisotropy of the solar wind constituents separately for the protons and the alpha particles. So we need a species-dependent angular distribution. So we need some way to separate the protons and the alphas in the solar wind. So based on this, we started looking at what kind of instruments existed or what kinds of instruments people had been building. So one of the common things that we found is that there's something called a top hat geometry electrostatic analyzer, which I'll come to in a minute. That is one instrument that is quite commonly used in different spacecraft, different missions. The other thing is angular distributions and of particles. So we started thinking in terms of what we were familiar with, which is namely the position sensitive charge particle detectors based on microchannel plates. And the other thing is separation of masses, so mass spectrometer of some kind. And the simplest mass spectrometer is really based on a magnetic field. So since on a space mission, space, weight, and power are all at a premium, we started thinking along the lines of a magnetic mass separation method. So let me just quickly tell you about this very common instrument on space missions. This is called a top hat analyzer. Now, a top hat analyzer is really an electrostatic analyzer based on the hemispherical geometry. So those of you who are experimentalists will immediately realize that these are just two hemispheres with a gap in between. And if you apply an electric field between these two spheres, you will have only particles of a certain energy passing through concentric with the sphere and emerging at the end. If the energy of the particle is too low, then it gets deflected inwards. If it is too high, it goes and hits the outer electrode. So only particles of a single energy can pass through undeflected. Now, how do you get particles into this gap? So for this, you use another guiding plate. And if there are any ions which happen to go your way, this guiding plate voltage will gently nudge these particles into the gap. So this is this kind of a device is called a top hat analyzer. It is based on 3 voltages and a somewhat complicated geometry of the hemispheres, but it does a very good job of getting a very good energy spectrum of any kind of charge particle that happens to enter this gap. So an electrostatic analyzer based on this geometry was something that was suitable for our needs. If you remember, what we were really interested in is measuring the proton flux in the Parker spiral, that I showed you, and these particles would come along in some plane somewhere. Okay. So let me just remind you of what we are trying to measure. We are trying to measure these kind of particles coming out. This is, of course, a not to scale diagram. So at any point along this, we could just place this instrument and have particles entering this gap. Okay. So particle comes in, gets energy analyzed, and reaches the detector. So the next stage is the question of how to differentiate between the species. So we built on this basic instrument and then thought that if we could place some permanent magnets, and create a region where you get a circumferential magnetic field, which means that the magnetic field is coming out of this page at this point and going into the page at this point. Okay, so this is the axis of symmetry. So think of this and spin it around this vertical axis. So you have a cylindrically symmetric instrument. So any ion that enters this trajectory gets energy analyzed, passes through this magnetic field. And because this magnetic field is perpendicular into the page or out of the page, the protons and the alpha particles will have different trajectories as they pass the magnetic region. Once they pass the magnetic region, you just get them to fall on a large area detector where you can read off the position. So the protons get deflected inward, alpha particles get less deflected inwards. So the proton can be detected from its position, the alpha particle can be detected by the second position. Okay. So this is the basic idea of the instrument. So one electrostatic part, one permanent magnet part, the upper part to do the energy analysis, the lower part to do the magnetic analysis. If you look at this from the bottom, so take away the detector, which is this slab over here, and then you will start seeing this detector from the bottom. These are wedge-shaped magnets, 16 of them placed like that. And through the gaps, you can have protons or alpha particles or any other particles coming in. And I've shown one such pair of trajectory here. The protons gets deflected to a large extent and alpha particles to a lesser extent. And they fall on the detector somewhere and you measure the position. And from that, you get to know what mass it is. Okay. But very soon we realized that this instrument has serious shortcomings. There are 2 serious shortcomings. The first one is that in order to sweep 20 kV protons efficiently into the detector, you need really very high voltages on the guide plates. And our electronics colleagues told us that it would be very hard to have on board such high voltages. The second part is that, which is actually the more crucial thing for our purpose, which is that in this top hat design, even if you apply very large voltages on the guiding plate, it is not possible to sweep all particles of all energies from all directions into the.
Bhas,
yes.
Can you go back to the figure, the one
yes.
slide back?
So,
What is the gap between the two electrodes, the analyzing hemisphere and
this
the
will be
ground?
typically 2 millimeters or 3 millimeters. So the radius is about 33,
Okay.
and the gap is 2.1 in this case. I mean, in our case.
Okay.
Yeah. So basically, what happens is that if you try to scan the angle energy phase space, then there are parts of the angle energy phase space which you can never access by simply sweeping this guide voltage, at least not in the region that you are interested in. And if you remember, at the beginning, I had said that our goal was to establish this anisotropy. So we could not afford to leave out certain parts of the energy angle space. So we had to have an alternative. And the alternative that we thought of was to have two of these instruments, but remove this curved plate and put a simple flat plate, but have two instruments. One instrument which had the magnetic mass analyzer section, and the other one which had only the electrostatic section. So this THA2, the top hat analyzer 2, is a purely electrostatic device. It has a similar detector, but it has only the electrostatic part. And this one is aligned across the ecliptic plane. And the first one, which has the magnetic separator, is aligned to the parallel to the ecliptic plane. So which means that THA1 has a mass separation capability. THA2 does not. THA2 looks perpendicular, looks at particles entering perpendicular to the plane of interest, and THA1 looks at particles which are coming in the plane of interest. So by having two of these instruments, we have achieved both our purposes, namely that we can look at angular distributions in the plane of the ecliptic. We can look at angular distributions in the direction perpendicular to that. And in one plane, which is the more important plane, which contains most of the interesting part related to the Parker spiral, has the magnetic mass separator and hence the species separation capability. Okay, so two instruments put together, and we get different information. The energy analysis gives us the energy spectrum. There is an accelerating stage which increases the range of particle energies that we can accommodate. There's a mass separator in one detector, in one instrument. And then there is a detector which is called, there are two detectors, one for each instrument. Both are based on microchannel plates. Okay. So now there are different ways to do the position readout for the magnetic, detector. And the method that we adopted is based on resistive encoding, which the experimentalists amongst us should be familiar with. So the idea is quite simple. If you have a resistive path and a charge, a bunch of charges falls on that resistive path, then this charge will disperse along the conducting paths and reach some point, and the amount of charge that is collected at the two ends depends on the resistance on the path, inversely proportional to the resistance along the path. So let's say this particle falls at some point over here, which is closer to this end. So there'll be more charge accumulated here than at some end of this path, which is connected up. So if I look at this on a bigger scale, let's say I have this sector, which I call B1. I start with B1, go in here, this is connected to this, it is connected to this, and back here. So B1 to B2 is a complete path. If a charge cloud falls on, say, this middle wedge, then because this path is shorter, you will have more charge on B1 and less charge at B2. And by looking at the distribution of the charge, Q1 upon Q1 plus Q2, you can get a fairly accurate calibration of your position of the impact of the particle. So this is all that we needed for our instrument. And then we started looking at various options for building this resistive path. Much of the ideas that are commonly used in laboratories for doing this are based on multi-layer coatings and things like that, mostly based on germanium. We tried this, but then we quickly realized that laboratory conditions are very different from space conditions. In space, you will have a lot of temperature variation, and these coatings are not stable against temperature variation. The resistivity changes very rapidly, so these are not suitable. So finally, we decided to go in for discrete resistors based on very fine, very fine machining and locating of these tracks and connecting these by resistors. So these are all discrete resistors. Each track that you see is only about 0.2 millimeters, and each wedge has 94 resistors soldered to that. It's quite a complicated, messy business, but this kind of a resistive anode works. For the second RAE, or sorry, the second detector, where the position information is not really needed, you only need the angular information. So one circle is all that we need to worry about. And again, we encode it using the resistive technique, and this is a much simpler design. So when it is all packaged, the THA1 looks like what this illustration on the left shows, and THA2 is very similar but shorter because the magnetic sector is missing. The magnets that are used in this are samarium cobalt magnets, each of them giving about 0.4 Tesla, 0.45 Tesla field. There are 16 of them, and all our calculations showed that this instrument should work and give us the kind of information that we need. Finally, the mounting of this instrument is going to happen in this fashion. There will be two of these top hat analyzers, one sitting on the top of a box or a tower, if you like to call it, and the other one sitting on the side wall of this tower. And all the electronics and processing electronics, high voltage, etc., will be sitting inside this box. So the THA1 has a footprint of 220 millimeters by 190 millimeters, this box over here. And this THA2 has a diameter of 160 millimeters. So this is a smaller thing, this is a larger one. And this instrument has a field of view which is, so these are the cutouts of the two instruments. This is the top hat 1 cutout. You can see the magnetic sector over here, the electrostatic sector over here, and the anode sitting over here, and the detector has been removed for this cutout. The THA2 is a simpler one, just the electrostatic part and a detector. The magnetic field is gone. The magnets are gone. Okay. So what we want to do now is to just look at what are the parameters that we wish to achieve, the observational parameters. Sorry, this should be 0.1220 kV, not 0.120 kV, 0.1 to 20 kV, with an accuracy of 10%. We want an angular distribution to be known, and the angular distribution is full 2 pi in 2 planes, and the accuracy is 22 degrees in one case and 11 degrees in the other case. So the vertical one has a much better accuracy. And species, of course, there is no limit on what it can accept, but it will only separate the species into protons, alpha, and the rest. So we are not, it's not really a mass spectrometer in the sense that people think of it. The resolution is just limited to separating protons, alpha particles, and heavier particles. You will see very soon some test spectra, and that will give you an idea of how good this is. Okay. And how do we measure this? So the energy of the incident particle is determined by the scan voltage on the electrostatic analyzer, and this scanning has to happen in a programmed fashion because these things will not be controllable from the Earth. We have to have programming on board in order to do the scanning. Then the angular coordinate of the particle hit is simply recorded on board and then dumped to the Earth Observatory or the Earth Center once a day or something like that. And the radial coordinate is also similarly read out, stored on board, and then dumped via telemetry at some point in the day. So this is how the instrument is going to function. Now, before we could say that this instrument was going to work, we had to do a lot of testing. And the stage one of this testing was just this simple single top hat analyzer in a small vacuum chamber, housing only the top hat analyzer and a 5 kV ion source. This was a commercial ion source, just a gun. Okay. And this stage, we could very quickly go through this stage and show that, I mean, as a proof of principle, that this idea works. I'm not going to show you too many spectra. I'll just show you one set of spectra at the end. Then came the stage 2, where this was like 2 years of work. And stage 2 was a more crucial stage because by this time we had to integrate all parts. So the electronics, the detectors, the housing, etc., everything had to be now combined. And this, of course, the combined thing is much larger than the top hat one alone. So if you remember, this is what the whole package looks like, including the tower. And this is just this THA1. Okay? So there's a huge difference in size. And what we really want to check is whether everything put together works in vacuum. All you need to do is externally give it 12-volt supply. All the high voltage generated there, all the processing electronics is inside. The detector biases are all inside. Everything happens here. And what you get out are just digital signals corresponding to the instrument observations that you are interested in. So 12-volt DC goes in, and TTL or whatever logic pulses come out. The whole thing goes into a vacuum system. That was a stage 2. So much larger vacuum chamber. All this was being done, has been done at PRL. We also needed an ion source which could go to 20 kV, which is the highest energy that we want to go to. So we had to build an ion source, float it to high voltage with the beam delivery optics coupled to this vacuum chamber. And in stage 1, we tested from 0.1 to 5 kV, and stage 2, we tested from 4 to 20 kV. We used different process gases just to make sure that our mass spectrometer is working. But in principle, just the proton and alpha, the helium would have been sufficient. Now, there's a whole set of other tests that come into picture when you are talking for space payload. And these are 3 really very, very difficult tests. So these are not something that we are normally exposed to, that that perhaps you don't even know about. The first one is a vibration test. So when anything is launched, it is subject to huge accelerations and a lot of vibrations also. So a vibration test is something that every payload has to go through. Now, a vibration test in this case was specified to be carried out in this fashion. So 14G is 14 Earth accelerations. 14G RMS value, but carried out randomly. That is the kind of acceleration or the oscillations that this payload has to be subjected to, with an amplitude of 12 millimeters up to a frequency of 100 Hertz. So this is quite a stringent vibration test. It's not just your normal rattle. It is a much harder test to pass. Then there is a thermal cycling. The entire payload has to go to 70 degrees, stay there for 24 hours, and then brought back to room temperature. The temperature on the satellite, on board the satellite itself, will be kept to fairly small range compared to this. The highest temperature that we would like the operating temperature to be about 30 degrees, or between 25 and 35 degrees. But the tests have to go to much higher temperatures. Then there's a radiation test where this entire instrument is, and particularly the detector and the electronics, is subjected to radiation testing. And after each type of these tests, so after the vibration test, after the thermal test, after the radiation test, the entire payload has to be tested again. So this is a very time-consuming and tedious process, but mercifully we have gone through all of this now quite successfully. Okay, so in the last 10 minutes or so, I'll tell you about what are the kind of tests that we have done and how does the instrument function. So here is a spectrum in which on the horizontal axis I have the track number. Okay, so now let me just quickly go back and tell you what track number means. If you remember this anode, then how much away you are from the center of this detector can be specified by the track number. Okay, so this is some track number. As you go from inside to outside, the track number changes. And different particles, if you remember this basic design, different particles will fall on different tracks. The lighter particle falls on inner tracks and heavier particle fall on outer tracks. So the track number is a measure of the mass. So let us see how we have performed and how the instrument has performed. This is the track number, and here are different mass spectra, so to speak. So forget about this coding, just remember that these different colors correspond to different gases being injected into the ion source. So Bg is background, He is helium, H2 is hydrogen, neon and argon. Okay, so when we inject argon and when we inject neon, you get essentially the same spectrum. So the argon peak and the neon peak are essentially the same. Now this is not surprising because if you look at delta n by m for neon and argon, it is way beyond the capability of our instrument. Neon is 20, argon is 40, and we are really only looking at the possibility of measuring or being able to separate protons and alphas, not neon and argon. This friend of ours over here is water vapor. This is water vapor, this blue peak, which is a very dominant fraction or contaminant in hydrogen, and that is showing up over here. This is helium. So if you look at these three peaks, this is proton, this is H2, this is helium. These are very well separated, and which is really what we want. We know that all of these heavier masses are going to be lumped together. We are in fact happy that we could even separate this water vapor. Of course, what you're seeing is at 4 keV incident energy. As you go to higher and higher energies, these peaks are going to merge. But we are satisfied that this separation of protons, I mean H plus, H2 plus, and He plus, is happening the way it was expected to happen. So we can have this nice calibration curve for a particular energy, and as you can see, as you go to heavier and heavier masses, the separation of the tracks is quite small. So this is an indicator of the mass separation capability of this instrument, and that performs reasonably. I mean, performs to the extent that we wanted it to perform. The other test is that of the electrostatic analyzer. So this is multiple spectra collected and put together into one graph. So different colors represent incident particles. So these are, and remember that for an electrostatic analyzer, the species doesn't matter. What matters is only the charge, the energy per charge, the E/Q ratio. The mass doesn't enter the picture. So these are particles of different energies being shot into the electrostatic analyzer. And as you can see, as a function of the electrostatic analyzer voltage, which is really the discriminator for the energy, you get very sharp peaks corresponding to different energy particles being shot. If I shoot a 4 keV particle, I get a very sharp peak at some point and nothing around it. Similarly, for a higher energy like 14 keV, I get a very sharp distribution at some value of the electrostatic analyzer voltage and nothing on the two sides. And as I go to higher and higher energy, the apparent width of the distribution keeps on increasing, width of the peak keeps on increasing, but the ratio delta E by E remains constant. It actually turns out to be 8% compared to the 10% that we had hoped for. So the electrostatic analyzer is doing very well. We have slight worries about our mass separation capability at the highest energies, but that is not terribly worrying because most of the action is expected to be over by 10 keV. Okay. So these are the two main function tests that we have performed. Of course, I'm not showing you all the spectra that we have obtained so far, but we are very happy about, especially about the electrostatic analyzers. So we are very confident about getting the energy anisotropy because our energy calibration is very good and the electrostatic analyzer is performing better than expected. Okay, so when this whole thing goes on board, we are going to have to worry about how to operate the instrument. As I said earlier, we need to do a programmed scanning of the electrostatic voltage in order to achieve, in order to obtain the energy spectrum. And we have two modes of operation. The first mode is where we have each step lasting for 450 milliseconds and another mode where each step lasts for 50 milliseconds. Then there are various other things which are not of great interest. But remember that we are going to do this scan with 50 steps. So we go from 0.1 keV to 20 keV in 50 logarithmically equal steps. So remember that our delta E by E is constant, so having a log step makes sense. And with this kind of scanning, we are going to be generating about 3 kilobytes of data every second, and one full scan time is 25 seconds. In the burst mode, which is the faster mode, we will have this happening at 5 times the rate. Now, what is the purpose of these two modes? Now, these two modes are basically designed to be able to see rapid solar activity. I mean, if there's a rapid solar activity, change in the activity of the sun, and we want to do some very quick sampling, we should be able to switch the mode to a faster scanning. Otherwise, stay in mode 1. Now, how is this changeover going to be implemented? So for this, we need a lot of telemetry from the ground station. And this telemetry, the telemetry program or the telemetry protocol has this mode switching option built into it. Then there are some safety aspects and other onboard operations that will have to be continuously monitored. So one of the things that we will obviously monitor is the count rate on the two detectors. And it can happen that when there is increased solar activity or for some other reason, the count rate on the detector suddenly goes very high. And this can be dangerous for the instruments. So we have some onboard logic which will switch off the high voltages autonomously if a certain activity is detected. Okay. So the reason why this needs to be autonomous is that the communication time between the satellite and the ground control station is 40 seconds. And by the time it comes to the user, it can be several minutes. So you really need onboard autonomous decision making for some extent. So the peak flux that we are talking about is not very high. It is about 5 kilohertz at the peak of the spectrum with a 10% energy pass. It could go up to about 7 kilohertz in some cases. But if it goes something like 4 or 5 times this, we need to be careful and switch off and switch back on the high voltages. The other thing is that which we'll have to worry about in the long run is that the microchannel plate really has is not a very well proven detector in space, and it may degrade. So we may have to keep monitoring its leakage current, its dark count, and things like that, for which we have provisions on board. And this detector the detector bias will then be changed by using a telecommand if necessary. So these kind of monitoring operations will also have to be done for this instrument, and this will be really a continued or a continuous monitoring and continuous operation. So to summarize, we have built this payload which will go aboard the Aditya L1 mission. It will have these two fields of view. One, this vertical gray disk. We are again looking at the satellite as if we are sitting on the sun. So this vertical gray disk shows one field of view, and the other one shows the other field of view in the plane of the orbit. By measuring the angular distributions in this plane and the species separation, as well as the energy distribution in the two perpendicular planes, we hope that we will be able to answer some of the questions that we set out to answer. These payloads have cleared all the environment tests. The desired energy resolution and the mass separation has been achieved. And the flight model, so what we are working on is what is called the qualifying model. And the flight model is awaiting assembly and integration into the spacecraft. And this is expected to happen very soon, COVID permitting. The launch date is sometime middle of next year. And I hope that a year later, I'll be able to tell you that this has been successfully launched. After the launch, it is a 6 months wait, during which we'll have no signal from the instrument, and it will be switched on much, much later. So it's a matter of a couple of years before, or maybe not couple, but more than a year before we can hope to get some information from this instrument. Thank you.
Thank you, Bhas, for this very nice presentation. And now the talk is open for discussion. So if you have any questions, I would request you to please write down your question or your name in the chat box, and then we can take up one by one.
Aditya, should I stop sharing the screen or should I leave it as it is?
I think leave the screen.
Leave it? Okay. Yeah.
So I can see. Yeah, I think SVK has a question. Yeah, please go ahead.
Hello, SVK. Hi, KK.
I think maybe his audio is not working for time being. We'll come back to it. There's another question from David.
Yeah.
David, you want to ask it or should I just repeat it?
Yeah, how will the instrument be positioned in space? Yeah, okay.
Yeah.
So, as I said, the approximate point where this satellite will reach is the first Lagrange point, which is 1.5 million kilometers away in the direction of the sun. And this satellite will do some kind of not a random walk really, but some kind of a Lissajous figure in a plane that is perpendicular to the Earth-Sun axis. So it will have some small meaning. It's not small on Earth scale, but it is small on astronomical scales. Small deviations from this point, and the satellite will have various mechanisms like thrusters, gyros, and so on, in order to remain pointed in one particular direction. Yeah. So what is the expected signal to noise ratio? Yeah, that's a very good question. The signal to noise ratio is going to be a very strong function of the energy of the incident particles. So at the peak of the energy, this ratio could be well in excess of 20. But at the tail of the distribution, it will be quite poor. I mean, it could be as low as 4.
Okay. Okay. Maybe I can ask a couple of questions.
Yeah.
So one is when you mentioned the payload goes through radiation test, yeah. Right? So I mean, what kind of test is it? In the sense that are you just testing the its integrity in radiation environment, or also its functioning in the background radiation?
No. Only the integrity. So it is not in operation when it is under radiation. So the tests are not being performed while it is being radiated. It is exposed to radiation, and its integrity is tested by doing the whole set of tests after it is brought back from the exposure.
Right. So then the follow-up is, once it goes in the space, yeah. How is it going to handle the normal cosmic ray background as well as the solar radiation?
Yeah, sure. So the cosmic ray background is much smaller than the proton flux. That is one part. And so that's why I said that the signal to noise ratio can be quite poor in the region where the proton flux itself is small. So this will, I mean, there'll be a constant cosmic ray background, and when the amount of signal it will leave on the channel plate is also going to be small, although the particle number incident flux can be quite substantial. That is how it is going to be very poor. I mean, it will result in a very poor signal to noise ratio in some parts of the spectrum. There's nothing we can do about it.
And second question that I had was, once you say that there could be fast activities from sun, and during which you have to close down or you want a faster scan time. So what is the time scale of, at what time scale you have?
Yeah. So when I say faster, greater activity on the sun, typical observations show that typically this activity lasts for a few days. So there we have enough time to respond from the Earth. But when there are sudden flares which result in sudden burst count rates on the detector, we need autonomous decision to shut off the detector. But to switch from one mode to another, we actually have plenty of time.
Okay.
I mean, hours, not seconds.
Okay. Thanks. Okay. I think there are a couple of more questions.
Yes, there are a couple of questions. One is MCP is very fragile. Yes. How do you manage all the vibration? So this is actually just better mounting, and that's really about it. I mean, there's not much else that we could do about it, because the entire area of the MCP had to be open, in the sense that there's nothing we could do to clamp it better. To prevent a large area being exposed or anything like that. The whole thing had to be exposed. We just improved the mounting, that's all. Yeah, then the second question from SVKK is about there are other methods to sense positions like optical methods. Why was the resistive anode chosen? Yeah. So optical methods, you mean phosphorescence and things like that. But phosphorescence, we realized that the weight penalty on this would be considerably larger, because you not only need the phosphorescence, you not only need the phosphor screen, but you also need the camera and things like that. But that could have been one possibility. But among other methods to sense positions based on charge division, the resistive method was more robust, particularly from the point of view of temperature fluctuations. Then, yeah, Vijay Shoday's question is, what is the plan of analysis of data every day? Okay, so these the data pipeline is still being worked out. The ISRO, the ISSDC, the ground station, will be the repository of the data that is coming in. There's a certain rate at which rate or certain time cycle over which data from different instruments will get dumped to the ground station every day. And then now what is being planned is that this data in the raw form will be available to the people who are developing the instruments, and curated data will be out in the public domain after a certain period. So there is going to be a monitoring team which will look at the raw data and very preliminary analysis to see whether we need to change modes of operation or make any changes to the instrument parameters and so on. And this will be monitored around the clock.
Okay.
The third one is, which will be the plane of angular variation? No, so the planes are actually fixed. There are two planes in which these measurements are made. One plane is the plane of the ecliptic, and the other plane is the plane perpendicular to that. Oh yes. Yeah, here is a question which is a very good question. So what does grounded mean in terms of ground voltages mean in terms of this of a spacecraft that is not connected to Earth? Yeah, so yeah, this is a tricky question. So ground could actually mean 50 volts. Okay, but it is basically referred to the spacecraft body. So the spacecraft will attain a certain potential, and it can keep on attaining. The potential on the spacecraft can change, and it can be quite large once it is in space compared to when it is on the Earth. So there are ways to, there are mechanisms on the spacecraft to distribute this charge and make sure that the surface is an equipotential. But it is not grounded in the sense that we normally understand. Yes, so the energy is relative. Yes, in a sense, the energy is relative, but that's the best we can do.
Aditya, there is a question from Professor Udit. Go up.
Oh, yeah, I think yes.
I think I answered that.
Yeah.
I think I answered.
Signal to noise ratio, right?
Yeah.
Okay.
Okay, so I do not see any more questions. Right. So, okay, so in that case, on behalf of the society, let me thank Bhas once again. And I would also like to thank all the audience members for joining us for this colloquium series. We have a couple of colloquia lined up in the next month. On September 4th, we have a colloquium by Professor C.S. Unnikrishnan from TIFR Mumbai. And then on 18th September, we will have Professor Uday Thevar from VII Institute in Israel. And the details of it will be sent to you in due time. So I hope you all can join us there. And with that, I would like to close this session. And thank you all once again.
Thank you, Bhas. Nice.
Okay. Yep. Thanks.
Thank you.